Hello, I am Andreas Zeller. I'm the author of the debugging book, and I'm here to present you a new chapter. This chapter is about finding failure causes in inputs. Situations as follows. You have a program, and this program has a large input, and then it fails. Boom. Good. Then you're in trouble, because if you want to debug your program with this very large input, well, you're in for quite some time, because typically as your program churns through the input, this takes longer, you get a bigger context, there's lots and lots of state that builds up, and execution takes lots of time. For instance, if you have a loop that actually processes through the input and you want to step through that, this is going to take ages. So a common technique as it comes to debugging, before you actually start going into the program code or doing anything with the program, is trying to figure out what exactly in this long input causes the failure. And the common technique for that is called reduction. The idea is that we want to reduce this long input to a minimum that still causes the failure, thereby removing all the other context around, all the unnecessary stuff. We can get rid of that. We pinpoint the failure cause as a very small input. And this has the advantage of us having to deal with only much smaller executions. And it gives us frequently a good hint on why and when the program fails. So let me illustrate that with a little program here. Now I'm sharing my screen, so let me share my screen here. Oh, which one is it? Is that one? Let's hope so. Okay, let's try. Yes. So Johannes, now you should be sharing. Now you should be seeing my screen. Okay.
Yeah, I see a screen.
Wonderful. And if you see a screen with the wonderful words reducing failure-inducing inputs, then this is actually the correct one. Okay, so this is the chapter we're talking about, and I'm going to illustrate that with a simple example in the very beginning. We're having, this is actually the ongoing program in here. We're having a mystery function, and this mystery function, which is deliberately written to be somewhat more obscure. So it's not exactly, so you cannot exactly directly see what's going on here in the program. But this mystery function sometimes passes and sometimes fails. And we actually, in order to find out when it fails, we are using a fuzzer. For those of you who've been in my automated testing course or have been reading the fuzzing book, a fuzzer is a tool that automatically produces random inputs. And in this case, we produce random inputs until it fails. This is a super simple fuzzer just in 5 lines of code. And it produces a couple of inputs, random inputs such as these. And this is what we do. And then it fails. And this is the failing input. Well, it's not exactly a large input, but it's obscure. Actually, if you use fuzzing inputs, they are typically always obscure because, well, they're simple random characters appended together. And the question is, what in this 26 character long input is it that causes the program to fail? Now, there's a sort of straightforward way to do such things manually. What you can do is, well, you can simply try to take out individual characters out of this. You can try what happens if I put in just the first half, what happens if I put in just the second half, and so on. But such manual debugging, well, you need a text editor for that in particular. Well, here we just have 26 characters, right? But if you have 1,000-line input, that's super, well, that's super painful. It's not exactly rocket science, but it's something that it's a very boring task that is actually much easier left up to a computer to do. So our task is to find out, is to reduce this input to a minimum that still causes the program to fail. And what we get here is invalid input, by the way, if we feed this in. And the question is, do we have a substring of this long string here that still causes the same failure? The technique we are introducing here in this chapter, we're going to skip the part on manual reduction. The technique we're introducing here in this chapter is called Delta Debugging by Zeller 2002, about 20 years ago. I know this guy. He is super pretentious and thinks that with 5 lines he has invented the world. So Delta Debugging is a technique that actually takes such a set of inputs, strictly speaking, a set of circumstances that either can be there or not. So let this simply be characters. And it reduces this input to the max by means of an automated test. Let me show you directly how this works. This is actually one of the simplest algorithms we do have in software engineering. I always say it fits on one page. This is a short implementation of Delta Debugging dd-min for reducing things. And it always fits. If only we would get rid of this assertion and this comment, then it would actually fit on the current screen. But it's really, really a very short algorithm and a very short implementation. The formal definition of Delta Debugging is a 5-liner. And and Delta Debugging in this form takes a test. And the test has 3 different outcomes. It either returns pass if the test passes, if the failure is not there, or it returns fail. Well, that is when the error is there. Or in the case that it fails, but fails differently, then we have the special value unresolved, which is being returned. And this is all we need. So we need a test that either returns pass, fail, or unresolved, and an input that originally failed. So here I am, and I'm invoking the dd-min algorithm. So we invoke it with our test, we invoke it with our failing input, we tell the function that we want to apply this input to, and we also provide the exception, that is the exception that we're looking at. And if I execute this thing, what we get is this. Takes I don't know, maybe 1/10 of a second or so. And what Delta Debugging does is, and you can see this very neatly here, is it runs a number of tests on your input with various subsets. So this is the original input. This is the one that fails. We know that already. And then what Delta Debugging does is it takes away chunks of the input and checks whether the input still fails. So here we have a chunk where this is the second half of the input. This is the input with the first half removed. It passes. And this is the input with the second half removed, and it also passes. So in that case, actually, this is where Delta Debugging differs from, say, a general bisecting algorithm. In this case, what Delta Debugging does is, if it cannot get further, that is, if it cannot get failures by removing large parts of the input, it keeps on removing smaller parts of the input. In this case, it removes the first quarter of the input. And when it removes the first quarter of the input, the failure occurs, which is great because now we have reduced the input to 3/4 of its original length. And then it continues removing quarters from the reduced input. This actually also works. So we're getting here down to another failure. Now we are down at 1/2 of the original length. We can continue doing that, and then we can still remove the smaller parts and still smaller parts. And in the end, Delta Debugging still reduces the size of these chunks that are being removed. And in the end, it actually tries to remove individual characters. So at the very end, what we have here is an input that consists of opening parentheses, 7, and closing parentheses. And this fails. And then it tries to remove the first character, the second character. Oh, it removes the second character, and then it still fails. And then it still tries to remove things. Maybe we can remove the first character. No, we can't. Can we remove the second character? No, we can't either. And now it has reduced the input, the failing input, which we had up here, these 26 characters, to just 2 characters. And by the way, this is the spoiler. Sorry for spoiling all the fun. This is exactly the smallest possible input that causes our mystery function to fail. If we go back to our original mystery implementation, let's take this one. What this here actually is an encoding of an opening parenthesis. This is an encoding of a closing parenthesis. And what we have in here is if there is an opening parenthesis and a closing parenthesis, and the opening parenthesis precedes the closing parenthesis, then our mystery function fails. Well, in all generality, the failure conditions will not be as clear as we have them here in these obfuscated lines, but still, Delta debugging is going to do a good job at reducing things. It is not exactly so. You may wonder how many tests does this actually take, and if all of your inputs either pass or fail, if all of the inputs fail eventually, then obviously it's logarithmic, because with every single step it reduces the input to a half. The main factor is how big is the last part that is irreducible, such as these 2 characters over here, because in the end, Delta debugging tries to remove every character one at a time, and this can actually take time. But it all depends. Also depends on the speed of your test. Delta debugging assumes, well, that you have time. In particular, you would run such a Delta debugging run together with a fuzzer or overnight or whenever. So you have a fuzzer produces long, complex, whatever inputs. And whenever something fails, which actually is not that often with a fuzzer, you can still afford to run Delta debugging overnight, and it will happily produce you with a very short input string the next morning. So this is neat already, but we can do better than that. In particular, this is something I'm doing here in the next. So we just had 20 lines for Delta debugging, and now we are setting up a big infrastructure that makes it easier to use Delta debugging, because we don't want to invoke Delta debugging with all these parameters every time and write a test and everything. So I'm setting up an infrastructure here, which you may or may not want to look at, that actually goes. We even generalize the Delta debugging algorithm into 3 variants: one that minimizes inputs, one that maximizes inputs, and one that looks for a minimal difference between 2 inputs. We're going to reuse this next week as it comes to applying Delta debugging on changes. But the important thing is what we're having down here in cell 82. Here we go. This is how we can also use Delta debugging, and this is one of the shortest ways you could ever think of using a Delta debugger. What this Delta debugger class does here is it observes a function call, namely this one, our mystery call, and it assumes that it assumes that this function call that is being observed fails, that is, it raises an exception. And then with this information, it already has all it needs. It knows how to invoke the function. It knows what the failing input is. And since this fails with an exception, it also knows what kind of failure to check for. And so all you have to do is you prefix your failing function call. Well, I guess you need to have a failing function call in the first place. And also important, one of the parameters of this function call has to be some collection that is a string or a set or a list of things. You can also have multiple parameters that all are sets and lists and Delta debugging. Then this Delta debugger is going to apply Delta debugging on all of them. And what this thing does is then, so we can do this in 2 steps. First, You invoke the Delta debugger over here. Boom, nothing happens. Now it has observed that this mystery function has failed. So far, so good. And when you output the Delta debugger, DD here in that case, it automatically runs and produces the failing function call. Boom, that was fast. So it simply tells you if you invoke mystery with an input that is two bracket, opening parentheses, closing parentheses, there you go. Couldn't be any simpler than that. Couldn't be any simpler than that. The implementation is well more complex than that, but you can have lots of fun. And again, you can also there's also parameter. You can set log to true, and then you're going to see what the individual steps are doing. Actually, when you're simply invoking Delta debugger like this, it only observes what has happened. So in this case, it tells you we have seen the mystery function with this particular parameter, and you see the exception that happens. And if you now go and run DD, then it actually tells you the individual tests that it runs. And you can see that it now processes the first parameter, which is INP input. You again see the individual steps of Delta debugging, and eventually it tells you what the failing call is. But normally you don't need logging because, well, because you can simply you can simply use this as over here and have fun with it. And there you go. This is very simple to use. And there's some effort in this simplicity, I can tell you that. But it's definitely fun, and there's quite a number of applications of Delta debugging which you can use. Let's go to give you a couple of examples here, just because this is so neat. We had not only the mystery function, but we also have our remove HTML markup function, and we want to figure out when this fails. Well, it turns out that this fails as soon as there's a single quote, as soon as there's a double quote and a closing tag in the input, because that already suffices for the failure, because our error was that it would erroneously remove double quotes from the input. And for these two characters already suffice. Here's another example. We have a function that takes two arguments, and it fails whenever whenever S1 is a substring of S2, and we put in foo bar and foo, and then this automatically gets minimized to two parameters, namely the first string is F and the second string is F2. That's all you need. And you can also go directly and combine this with the debugger interface that we've seen before, because you can actually get these arguments and immediately invoke your function with these reduced arguments. And then you do this with your interactive debugger, and then your debugger starts and you can print out individual parts, further examine things. There's lots and lots of potential in there. Finally, another usage example, and I would very much encourage you to actually look into the implementation of both the Delta debugging algorithm as also into the ways that we are collecting those function calls and later using them. But in the end, we have a very nice and neat application of Delta debugging, which is rather rarely seen, but which actually is going to form the base for the second project that we're currently preparing for you. So here's an extra incentive for you to look carefully. What we're doing here is we are using the program code as input to Delta debugging and try to find out not only what the minimal input is that causes a program to fail, but actually what the minimum program code is that causes the program to fail. Now you wonder, why would I want to do that? Well, two reasons. A, because program code can be input to, for instance, to a compiler, an interpreter, or generally anything that processes input code. And this is where you definitely want to have small parts, because if I am going to feed, say, 100,000 lines into a C compiler and then it crashes, I am not going to go and debug the C compiler with 100,000 lines. I want to have 2 lines or 3 lines or 4 lines at most. I want to have a minimum input to find out what's going on. And there's actually special variations of reduction algorithms that are specifically tailored towards program code. However, even in our simple example, even a simple algorithm like delta debugging does the trick. Let me give you a simple example. Here, we are reading in an entire module, the source code of an entire chapter, which is, I don't know, 400 something lines. And we want to find out which part of this chapter actually causes the function remove HTML markup to fail. And you can apply delta debugging on that. And if you do that, this is what you're going to get. So this is all it takes to get remove HTML markup to fail. And what you have here is this is just incredible. It's a single line of code which fails. Well, at least it produces none, and none is not a valid output, so it fails. Boom. And this is what you get when you reduce these 436 lines to the small part that actually is failure inducing. These are the 4 lines that remain. You wonder how it comes that we have 2 more lines in here. Well, that is how delta debugging works. It tries to remove individual parts, which in this case are lines. And if you remove this line, you're going to end up in an invalid program, because then this function will have no body anymore. And if you remove this line, then the program will also be invalid, because this line is indented and you cannot have an isolated indented line in Python. So this is weird already, but keep in mind that it already has identified that our tests actually looks at remove HTML markup, and well, in order to get it to fail, you need to be able to invoke it. And yes, this is the relevant line in our entire chapter that is actually related to that. We're going to improve things a bit down here, and then we actually add another test that the function actually works. And then we again remove, and then we again apply delta debugging on it. And then delta debugging very neatly produces the source code of remove HTML markup, which it automatically extracts from the much longer 400 line chapter. And this is actually the full source code of remove HTML markup, and this is relevant for producing the failure. Actually, if you look closer, this is also fun. You will find that this is not exactly the original source code, because a couple of blank lines and comments and assertions have been removed because none of them contribute to the end result. Again, an effect of delta debugging. Real fun comes when you apply delta debugging not only on lines of the input, but actually on the characters of a function, which we do here just for fun. And this also again shows you how reduction works. Because if we take this source code and apply delta debugging on it, on the individual characters of that string, this is the function we get. And this is really fun. This function still has the same feature as the original, in that it works on inputs without any quotes. And it also, as the original, removes quotes from the input, but it does so in a different way. So in the original, we have the tag and quote are Boolean variables, which are initialized to false. Well, it turns out that you can simply write tag equals quote equals out equals an empty string, because an empty string in Python is equivalent to false. So let's just remove that stuff. And here, I didn't even know you can do this directly after the closing quote. You can leave out the space, so that works. And also look at that, it has removed a new line. So everything that is superfluous has been removed. And this is really weird. If there is a double quote in the input, all this thing does is quote, which is an expression which does nothing. But this is precisely what our failing remove HTML markup function does, namely nothing. And there we can just as well have quote as anything else. This is whenever I'm applying delta debugging on something I didn't know before, I'm sometimes astonished at the results. And yes, this is the smallest possible function that works like our original buggy remove HTML markup implementation. The smallest, however, here in this case refers to characters. If you remove any character from that code, it will no longer be a valid Python function, or it will no longer work as the original. But instead of removing characters, you may still be able to remove larger parts, say keywords and like things. So delta debugging is not an optimal algorithm in the sense that the result is absolutely the minimum, because in order to figure that out with tests alone, you would have to test each and every subset of these, whatever, how many would that be? Some 50, 60, 80 characters or so. And if you want to test all the subsets of 80 characters, you're in for the factorial of 80, if I recall it right, number of subsets, so not going to work. All the delta debugging gives you is that removing any single character in here is going to remove the failure. You can do better though by reducing not only at a lexical level, as delta debugging does, but actually reducing structurally at a syntactical level. To this end, and this is how this chapter ends, we're going into tree reducing. We're looking into syntax trees, which is the internal representation of program code in any program that typically manipulates, transforms program code at scale. Compilers, interpreters, parsers in general, all work on tree representations of code. The nice thing is that with Python, you can very easily transform a piece of code into the appropriate syntax tree. And here's the syntax tree for remove HTML markup. You see what you have here is that this tree consists of a function definition, and this function definition starts with a string, which is the name of the function. It has a number of arguments. Well, number is good. It has one argument, which is named S. And it starts with an assignment, namely an assignment of the value false, which is a name constant, to the variable tag. The next statement in our function definition is another assignment, quote equals false. And then we have out equals a double string in here. And we have a for loop, and the for loop has a body, which consists of an if. And you see, this is the entire tree that comes out of that. And the interesting thing is that we can now go and systematically reduce the function by systematically replacing parts of that tree. And after we're done with that, we can convert the tree back into our original function code. And I'm going to cut things short here, but here's an example of what this looks like at the very end. So let me just find this at the very end. Here we go. We reduce the tree, and we actually implement a couple of extras such that we can replace statements by individual pass statements. We replace ifs by body and whatnot. And this is what we get when we apply all these node transformations. And you see that the code has become even smaller, not so much lexically smaller, but syntactically smaller. For instance, we have been able to remove all the references to quote. So the original assignment quote equals false is no longer there. The setting of the quote variable is no longer there. Checking if C equals less and not quote has been removed to if C equals a beginning of tag and end of tag. And all these, we could even go further with that. We could go and say, okay, I could go and also remove this pass statement because, well, pass does nothing. We could also go and say, okay, if C equals quote, oh, the single quote checking also has gone. All of this has been removed, and none of this is relevant for producing our failure. So syntactically, this is already very small, but you can make this even smaller. And this is why we're having our second project, which will go out by the end of this week, where we will give you the assignment of taking even already reduced parts like these and making them even smaller by removing if branches, by removing statements on their entirety, and trying to get this code as small as possible. If you build something nice, generations of Python compiler developers are going to kiss your feet. Well, maybe not kiss your feet, but still, you will be in the you will be in their prayers and thoughts because you may be able to thoroughly help them. Um, so, and with this, we're already done. This is all about reducing failure-inducing inputs. Go and check out the original. Go and check out the original papers with all their discussions of how to reduce things. Also, we have added a couple of pointers to papers that give you ideas on how to reduce program code. And I wish you lots of fun using this infrastructure, both to both as part of your studies, as well as it comes to as well as it comes to actually apply them in your own code whenever you have a function that suddenly fails on some big input. Well, Delta debugging to the rescue with Delta debugger as DD, and there you go, and you get a diagnosis. That's all for now. Thank you very much. And I guess we'll see each other next week.